Then next participant, if he is in the meeting, I saw Willem from Dutch Fig.
Yes. Can you hear me?
Excellent. Go ahead, William, with NOF, a tiny file system for SPI Flash chips.
Yes.
Go ahead.
I have to share the screen, so okay.
And a lot of thanks to Ulrich and Christian Hinze for making those questions, and everyone who participated. It was very, very interesting.
Okay, is it clear? Can you see the sheet?
Yeah, try again.
I have started sharing and I have opened my PDF.
Yeah, so try it again.
Okay, I will try. And then, any better?
Yeah. Yes.
Okay, then I'll start. I'll tell you a little bit of NOF. That is a small file operating system for SPI Flash chips. I had built a button like you see here in the example. That's a brush that you can wear when you go out or do promoting yourself, and it shows small animations on screen. And those animations I had to store. So I needed some sort of file system. That's why I designed NOF. I have still another example over here. This is a small Flash programmer. It uses a bootstrap loader mechanism, and it can store files in different formats on the Flash chip using NOF operating system. And it's meant as a portable programmer. It uses a small OLED screen to select the file, and when you press start, it selects the right protocol and goes on flashing your microcontroller. That's the idea behind it. Now you go on. This is the used chip. It's a small SPI Flash chip, and you can get it from about 512 kbyte to about kbit to about 128 megabit, if I say it correct. On my prototype, on this picture, you see the OLED and an SPI Flash chip. That's a 2 megabit version. So there fits on the chip fits 8,192 256 byte sectors. So that's about what you can store on it. And the mechanism can address a maximum of 60 megabyte. That is the 128 128 megabit chip. So that's where it's targeted. And about Flash chip, the reading can be done in bytes. Writing is done in 256 byte sectors, and erasure is done in 4096 byte sectors. So that's quite a difference. And I take the structure of the Flash chip leading for the design of NOF. Now a little bit about the design. I use the first sector for the file entry table. I use this FET for setting off. From 0 on there are file IDs. From C00 there are the directory IDs. So we have a FIT for the files and a DIT for the directories. The formats of the file IDs. there are 4 cells for each file. The first cell gives a pointer to where the file is stored, and that pointer is given in sectors of 256 bytes, and it's also used as a file ID. The second one gives the directory hash. That's the directory hash with the complete path to where the file is stored. And the last one is the file hash, and it gives the hash code of the file name. I have done this because I wanted to use the area in the small flash chips efficiently. Finally, there's the file length, and it's also given in sectors. So the file length of this one is 30 sectors. Now, you see some more files. The second file has a directory hash of 0. That means that it's in the root. Then we have an erased file, all zeros, so quite simple. And we know if it's free when there are all FFs in the cells. The next one are the directory IDs. The directory IDs using 16 bytes record format. The first cell is again a directory hash. You can it's the same that you see in this directory hash table in the file ID record. The second part is a 14 bytes name. And you can see that the directory source has a 73CB hash code, and you can find it in that file 0 is stored in that directory. So then you can see a little bit how it works. Then what's the format of a file? The first sector of the file of 4096 bytes. Again, the array sector we use as a minimum format. The first 2 bytes contain the fit. That's the file identifier, and an aux byte where you can give some special information about the file. I use this for movie files, and then it contains the number of frames that a movie has. And finally, the file name of 30 bytes. This file name can be quite long, and the rest is file data. And all other records of the file are behind it. They're always behind each other to keep it simple. Then we have a small explanation of what fit does, the file type. We have 6 file types until now: the Texas Instrument hex file, Intel hex, ASCII, a Forth source file, a picture file, and the general binary files. That's all I use for now. Yes, all zeros. The limits of the system, of this system now, are 384 files and 64 directories. That is quite small, but the flash chips are also quite small, and it's easy to change. When you want to change it, you can say, for example, that not only the first block is for the file, the FAT, but you can say also that the second block is for that too. It's quite easy to change just 2 constants. Then for the searching mechanism, I use CRC16 CCITT for that. And every file name and directory name is converted to a CRC code. And that's done by this little routine. If you want to know more about it, you can see on Project ForthWorks on GitHub. there we have a complete explanation about it. And even Uli is making some background information. Some processors do the same in hardware. For example, the MSP 430 has some chips have hardware CFC. That's quite convenient, but speed is of no importance when you type in a name and search for it on this small disk. You don't need any speed up. Then some small information about built-in functionality. There are a lot of more functions, but I would name a few. To connect an SPI Flash, we can mount it just like in Linux. You can define a new directory. You can choose a directory and show a directory. You can ask the contents of a directory. You can show a tree of all directories in the nesting from the path you are working in. You can view a file, you can include a file, delete all files and add files. And because this system runs on a small microcontroller, the adding files is a little bit different than you're used to, that we see at the end. Then we come to some small code examples. This is all NOF code, but it's not specifically written for NOF. You can run it anywhere. I wanted to give a small overview of the functions. The curly bracket open FL opens a flash, the command to the flash chip, and I marked those green, and it are specific commands for the internal state machine of the flash chip. For example, you see 3 here, and 3 here commands the flash to go in the read status. You can here see the command 6. The command 6 says to the command there a write command is followed. If you don't give the command 6, it won't write, even if you send a lot of data. And so on. Erase is command 20, then erase the sector with the address that's given on the stack. So now, again, the commands, open the command for the flash chip, define a cfetch command for flash. So this is works just as an ordinary cfetch import, but it's written from the flash chip, and it needs a double address because the flash is quite large, and if you don't have a double address, then you can't address the whole flash. Reading a sector, it's almost the same as reading a byte, again, only but you read here 100 bytes at a time in a small for next loop. If you, before you can read, you need to send the address that is sent here. You need to give the address of a buffer that receives it, and then it's just getting the data. Finally, we close the command. Then we have the write on. This, as we said, it was enabling the write to the flash. Then write the sector is almost the same. You give the command 2, you enable writing, and then you go in a loop and send out data. And finally, you have to wait until the chip says, I'm ready with writing. All the whole sector is written, and you can go on, continue. Now, erasing, as we said, was done in 4K byte sectors. So erase sector is any address within that 4K byte sector is good. First we say write on, then we send the command, the correct command, send the address, and wait until erasure is ready. So you see it's quite easy code. Here we have the two constants that define the fetch sector for the file IDs and the directory IDs. And then we have the main command, that's mount, that enables the SPI, enables some internal data for NOF. And then we go on scan the fit record to initialize it. What this does is it starts at fit, hector fit, and that's 0 here. And then it fetches the data until it finds FF. And then when it's FF, that's the end of the used part of the fit, and it just stores it in the value, except that it does a little check if it was filled and it overflows, and it initializes to the maximum size it has. Then we do the same with the directory IDs. It's also a scan action. And when you have the directory IDs, we just have to initialize the first free sector that can be used for writing for the next file. And it does that by fetching the address from the last used file name. So it gets that from the file record. We have stored the last free location, and because all records are in a fixed format, 16 bytes, it makes it easy to subtract 16 from it, and then address the correct address and calculate where the next free location on the disk is. And that's all it does. When there is nothing found, it starts at 10, and that's the first free block on the flash chip. And finally, it enables the directory system by selecting the root directory as a start. And that's all about this small introduction about NOF. I can show some commands here. The first command in green is mount. Now it's enabled. We can use the command there to show the directory structure on that flash chip. When we use tree, it shows all the subdirectories too. And the next one is using the view command. I wanted to use the setup of an OLED screen here, but I made a typo, and then the wrong hash was calculated, so it says file not found. And then a second attempt, I typed it correct, deleting the space, and then it just showed the contents of the file. Now the next one, here we see how files are prepared to send to the disk. Fourth column, and the name behind it becomes the file name in red. So this file is sent to the flash chip, and the 3 semicolons give the end of the file. So this part of the file until the semicolons become the ASCII file, and this is a small include file. Then we can use when we load it, it loads a complete OLED package with setup, 2 character sets, no, 3 character sets, a graphic character set, and a small AGL demo. Now to add hex files, for example, for the BSL programmer, you do the same. You have here a command that gives the signs for which chip it's dedicated to. So it selects the correct programming protocol. Then we select that an Intel hex file is coming with the name C2X55. And that's an MSP 430 FR chip. And then comes the Intel hex code, and this closes on the end record of the Intel hex. and then it's ready. Finally, I want to show you a little bit about how it works in real time. Here we have the contents of the current thing. That's one of my it's my prototype no forth button with animations.
Willem, we just see the slide.
Oh, sorry. Yes, I have to select another screen. Okay. New share. Yes, that's it. Sorry.
Yep.
Yes,
Mhm.
ready?
Yeah.
Okay, then we start again. I use a new boot up. That's no forth for the MCV 59X9. That's an FRAM chip. And it initializes it does mount on startup. You can see that too when you use in no forth we use an app factor for that. The app factor is just value, and when we do MC, that use there's a C on the address on the stack. Here you see the mount routine with the first setup. This has an extra setup for the movie player. And then we can use there because all is done, and we can use tree to see the directory structure. And we can you can select any. One of the things I did do here was to show that using the same name is no problem at all. You see here that the directory extra has a subdirectory trees, which has a subdirectory trees, which has a subdirectory trees. And it also goes correct because you start with the hash code for the root, then you add the directory extra, it gets a new hash code. Then you define in extra directory trees that uses the hash code from extra as a start, and so forth and so forth. So you can go on, and you have no problem at all. And it still is quite small. Here you see a list of picture files. And I wanted to show some other. You can use some regular definitions that you use in DOS or Unix. And so we go back to the root. And now I want to select tools and show you working. In tools, you see some port files. And I wanted to include one. The disassembler, it's called des. That's loading the include file, and now we have it in the system. You see the last words, das and mdas. So we can now decompile or disassemble the forth system. That's a small thing about the NOF file system. I wanted to show you one last thing. That is a small. I made a small movie of my demo version of the chip. Here you see the movie playing. That's directly from Flash to the OLED screen. This one I made for a comic book artist. When he goes on promoting his books, he wears this brush. So that's it. Any questions?
Nice. Thank you very much.